Welcome to Aryavat Center for Theoretical Physics. Today we will learn about the Schrödinger wave equation and how to solve Schrödinger wave equation in case of particle in a potential well. First of all, we should know about the momentum operator. Just like in the classical mechanics, there is a momentum which is called P, which is m v or m d x by dt. Same momentum becomes operator in the quantum mechanics. So px in the x direction, momentum operator P in the x direction will be minus h bar d by dx. This is momentum operator which acts on some wave function psi and gives some result. Now time independent SE equation for free particle. Time independent Schrödinger equation for free particle is minus h bar square 2m d2 psi x by dx2 plus vx psi x is equal to e psi x. Now for the free particle, potential Vx is 0. So this SE becomes this minus h bar square by 2m d2 psi x by dx2 equal to e psi x. This is the Schrödinger wave equation for free particle, and this is time independent Schrödinger wave equation. Now we will solve a case where a particle in the potential well. Let's imagine a particle in the infinite potential well. This is the particle which can freely move in this potential well. Inside this well, potential is 0, but at the wall the potential is infinite. So we have to solve the Schrödinger equation for this particle in a box. We can imagine this situation like this as in the classical picture, a ball going back and forth between these rigid walls. This is the ball going back and forth between these rigid walls. This is equivalent to particle in this infinite potential well. So in the well, potential is 0. So we can write this Schrödinger wave equation minus h bar square to m d2 psi dx2 equal to e psi x for x between 0 to L. Now particle cannot be found beyond the wall. The probability of finding the particle is limited in the box. We cannot find the particle beyond the wall. If x is greater than L, it means in this region or in this region, probability of finding the particle both in this both region will be 0. So psi x is 0, wave function is 0 for x is smaller than 0 and x is greater than L. So we can define the boundary condition. Boundary condition will be psi x is equal to 0 or x is equal to L is 0. Wave function for x is equal to 0 or x is equal to L is 0. Now we can solve this Schrödinger wave equation. Minus d2 psi dx2 equal to 2me by h bar square psi x. We can rearrange this term d2 psi dx2 plus 2me by h bar square psi is equal to 0. Let's assume that 2me by h bar square is k square. So the differential equation will become d2 psi dx2 plus k square psi is equal to 0. And general solution for this kind of differential equation is psi x is equal to a sin kx plus b cos kx. Now we apply boundary condition. This is the boundary condition. Psi x is equal to 0 is equal to 0. So x sin k 0, b cos k 0 is equal to sin k 0 is 0. It means b become 0. So we will get the wave equation for this particle in the box is psi x is equal to a sin kx. Again we apply the second boundary condition in which x is equal to L. So psi x is equal to L is 0 or a sin kl is equal to 0 or sin kl is equal to sin n pi. Sin 0 is equal to 0 is equal to sin n pi or kl is equal to n pi or k is equal to n pi by L. This is the quantized value of k. Now we can find the eigenvalue or eigenfunction of this Schrödinger equation. So in the next lecture we will find this eigenvalue and eigenfunction of the particle in this box.